All right, I'm going to talk about distribution of sample means. Central limit theorem stuff we're going to go over today, null hypothesis testing, and then we're going to talk about why it's all bad. You've read a couple of articles on this, so some of this stuff should sound familiar. Do make sure, though, that you're going through and reading the associated papers on the syllabus here. So up to this point, what we were doing last time is we were identifying the location of individual scores, individual values within a population of scores, right? So we're saying, doing problems like, I have an IQ score of 117. Where is the score of 117 in relation to all other scores in this distribution? This is fine. This is a nice thing to do, particularly for your clinical folks. You should continue to do this type of stuff, right? I have a client who has a score on a depression measure or an anxiety measure. This is their score. What would be really nice is if you could take that and translate that, assuming that you have a normal distribution in some sort of normative reference group, that you can say, this person is scoring probably in like the 85th percentile of people who are reporting anxiety on this stuff, right? So it's important, don't forget it. But for the purposes of our research, right, we're rarely interested in where an individual score is relative to others. What we're more often interested in doing is looking at inferences based on means from a sample of scores, okay? I don't necessarily care where Heejung's score is relative to everybody else, but what I might be interested is looking at the scores of all graduate students in management and marketing relative to some other population, right? And so just like we've gone through and determined representativeness and probability of extracting a specific value given a population of scores, we take this same concept, move forward, and what we can do is we can start looking at the representativeness probability of obtaining a specific sample mean given all other possible sample means that could be taken from the population. Same concept, we're just kind of layering it up here a little bit. Okay, and so what we're going to be talking about is distribution of sample means. Formal definition of distribution of sample means: distribution of means obtained from all possible random samples of a particular size that could be selected from a population. Okay. Look at this, make sure you understand this. This is an important thing to have a grasp on, right? Previously, as we talked before, we were just looking at individual scores. Here what we're going to look at is the distribution of mean values of all possible samples of a given size that could be drawn from the population, okay? The values in this distribution are means, okay? Now in practice, let's say we have a population, let's say the US population, we're just interested in American citizens, right? Countless, how many people live in the US? Anybody know? 20 million, something like that? Seem reasonable? I don't know, let's say it's 20 million, I don't know. And we wanted to say, grab a sample of 1,000 people. Say we got a big sample, right? But how many unique samples of 1,000 could you draw with replication from a population of 20 million? It's a lot, right? And so it's impossible to account for and calculate all these samples directly. Luckily, we have mathematics on our side and people who do this stuff for a living, okay? But just as an example, so you kind of see what's going on here. Let's say we have a population that doesn't have 20 million, let's say it has 4 people, right? It's a population of 4 scores. We have someone with a 2, 4, 6, and an 8. Mean of this population is 5. 5 doesn't actually fall on anybody's value, but that's what the mean is, okay? What we could do then is say, let's say we want to draw from those 4 individuals samples of 2 with replacement, okay? So that means that once we pull somebody out, we put them back and can draw them again. Given our 4 scores, if we want to draw samples of 2, 16 unique possible unique samples that could be drawn from those 4 scores. We could have 1 and 2, or we could have 2 and 2, 2 and 4, 2 and 6, 2 and 8, 4 and 2, 4 and 4, so on and so forth, right? So you can start to see, even with just 4 scores, there's 16 possible samples that could be drawn from that very, very small population. And then what we could do is we could compute the mean of each one of those possible samples in 2. So here's our sample, right? First draw, second draw with replacement, and then we go through and we calculate the means of all possible samples. If we take then and create a frequency distribution with the means of all possible samples of 2 from that population of 4 individuals, what we get is a distribution of sample means for n equal 2, okay? And this is just our frequency distribution. If we plot this out, these are all the means and the frequencies at which these means occur from that population of 4 individuals, okay? People following me up to this point, see what we're doing here? Any questions? Okay. Now, what we start to see when we do this, it doesn't matter how large our population is, we start to see certain characteristics start to emerge. First, sample means pile up around the population mean. Population mean of our 4 scores was 5, right? If we go and we look at our distribution of sample means, what's the mean of this distribution, Zach? 5, right? And so our distribution of sample means, the mean of the distribution of sample means, or our expected value of the mean, piles up and starts to pile up around the actual population parameter, okay? So the mean of the sample means will be the same as the population mean. That's sort of convenient. We also see that our distribution of sample means generally form a normal distribution, right? Our actual, is this a normal distribution here in our population? No. It's, how would we describe that distribution of scores? We call that a square distribution, right? They're just sort of out there. There's no actual sort of curvature. We've just got a value at each point, right? We would probably have horrible kurtosis, negative kurtosis if we were to run statistics on that, right? But when we go through and we create our distribution of sample means, distribution of sample means looks beautiful, right? Wonderfully symmetrical, it's very nice. And we see that even though we might have an ugly distribution in the population, when we start to calculate our distribution of sample means, distribution of sample means starts to become normal very rapidly. And what we can do then is we can use this distribution of sample means to start to answer specific questions about the probability of selecting a random sample from that population, okay? For example, here, probability of selecting a sample of 2 with a mean greater than 7. Can you tell me what that probability is, Candace?
It's low.
Yeah.
1 out of 16.
1 out of 16, okay. Essentially about a 6.3% chance. So if I go through, and I've got these 4 scores, and I reach around, and I grab one, pull it out, sort of register it, put it back, reach around, grab it, another one, pull out, the likelihood that the mean of that sample of 2 cases is going to be greater than 7, there's only one possible way that that can happen, right? And so because of that, I can take 1 divided by the total number of possible samples that I could draw, which is 16. 1 over 16 ends up being, again, about 6.3%, okay? This is how this works in a very small applied sample. What we can do, given sufficient mathematical proofs, we can explode this up and start being able to do this at a much larger scale, okay? So, principle that allows us to start to make some of these inferences, or so I guess I should stop here. People clear, sort of see what's going on with this demonstration and why this works? Okay. Central limit theorem is a mathematical principle or statistical proof here that's sort of working out sort of the mechanics of all of this. So our central theorem states that for any population with a mean of mu and the standard deviation of sigma. Distribution of sample means for a sample size of n will have a mean equal to the sample mean, or to the population mean, and a standard deviation of sigma over the square root of n, and will approach a normal distribution as our sample size approaches infinity. Okay. What we've got here is this is giving us the characteristics and telling us what the characteristics of our distribution of sample means is going to be. The mean of our sample means is going to be the same as the population mean, and the variability, or our variability in that distribution of sample means, is going to be equal to our population standard deviation over the square root of our sample size. So, for example, let's say I want to know, I'm interested in adult height, okay, and I have samples of 100. Distribution of sample means would be if I were to, and let's say my population is everyone in Wyoming, right? I'm interested in the average height of individuals in Wyoming. I'm going to collect samples of 100. We've got about 500,000 people in the state. That's a lot of unique samples with replacement of a sample size of 100 that could be drawn from that population of 500,000 people, right? But what we see is that this distribution of sample means starts to approach normality very quickly under one of two conditions. Okay, and this is important to keep in the back of your head. One, if the population from which the samples is drawn is are drawn is normal. Okay, so this is where you have to start thinking about your construct. Do we expect height in the population, adult height in the population of Wyoming residents to be normal? What do we think, Rachel? You think height has a normal distribution?
Yes,
Yeah.
probably.
Yeah, probably, right. And so the construct that we're sampling and we're measuring here probably has a normal distribution in the population, right? It's not something that's wonky. I would expect a relatively nice bell-shaped curve if we were just reading people's height, right? And so when we're, the population from which we're drawing our samples from, if that population has a normal distribution of scores, we start to see this distribution of sample means start to approach normality very, very quickly, okay? So even if we had a very small sample size, let's say our sample size was 10, distribution of sample means would still probably approach normality pretty quickly, given that the underlying construct that we're looking at has a normal distribution of the population. Okay. Sometimes the construct we're interested in doesn't have a normal distribution, right? Let's say instead of height, we're looking at marijuana use in the state of Wyoming, okay? In numbers of grams smoked or something like that. Are we going to have a normal distribution of that? What do you think, Judah?
Guess not.
Probably not, right? And this is one of these things that happens with certain types of substance use, different types of constructs. We don't get a normal distribution. Probably most people use 0, some a little bit, and then things start to skew out to heavy users, right? So in this situation, we don't have a normal distribution in the underlying population. However, the good news is that this distribution of sample means still approaches normality very quickly if our sample is 30 or more people, right? So if instead of adult height, we were looking at marijuana use in samples of 100, that's a large sample. And so even though our scores in the population, the distribution in the population is not normal. And if we were to collect a sample of 100 people, their scores would probably not be normal. But the distribution of sample means, right? The mean of each one of those samples. If I were to draw 100 samples, register the mean, draw another 100 people, register the mean, draw another 100 people, register the mean, the distribution of sample means would start to become very normal, particularly with a sample of 100 or more, okay? People sort of understand these properties and sort of how this starts to develop, okay? Central tendency, okay? Mean of the distribution of sample means. This is represented as the average of all possible means of a given sample size will equal your population mean. We refer to this as the expected value of the mean. This is the mean of a distribution of sample means. This is equal to the population mean. So here, random samples of adult height, I'm going through, collecting 100 people, measuring it, tossing them back, do it again and again and again and again and again and again. If I start to plot the frequency distribution of those means for each one of those samples, we would see that the expected value of the mean, 68 inches. Turns out the actual population value is 68 inches as well. So this is if we're looking at central tendency in our distribution of sample means. Also want to look at our variability, okay? And this is going to be incredibly important, okay? Standard error of the mean, right? Standard error of anything, but in this case we're talking about standard error of the means. This is the standard deviation of the distribution of sample means, okay? Standard error is the standard deviation or metric of variability in the sampling distribution that you're looking at. Again, here we're talking about means, but later on we can talk about other types of things, right? Your standard error, here in this case, standard error of the means. Standard error is your standard deviation divided by the square root of your sample size, okay? Couple of ways that we can attach a meaningful interpretation to your standard error. One, provides an index of how much difference to expect from one sample to the next, okay? So here's our distribution of sample means. Our standard error is our standard deviation of this distribution of sample means, right? And so we can look at that standard error and say, okay, my sample mean in this case is 70. If I got a standard error of 2, I can probably expect on average that if I were to replicate this and draw another sample, I would expect that on average any replication sample that I grab of this size is going to be about 2 points from where this mean is, right? On average. Now who knows, maybe you got a weird sample that's way the hell out there, right? But on average, if I keep going through replicating these samples, my standard error tells me how much distance I should expect from one replication to the next, okay? Again, this is the same thing, same interpretation that we would place on our standard deviation. It's just in standard deviation, we're talking about distribution of scores, right? Standard error, we're talking about distribution of means or some other test statistic, okay? We could also interpret our standard error as how well any individual sample mean estimates the population mean, right? This is our true measure of error. We could interpret our standard error as sort of across replications, how close or how far individual means will be from one another. I can also expect it or interpret this as how far my individual sample mean will be from the true population mean. Again, if my standard error is 2 in inches, I would say, well, I would expect my error to be plus or minus about 2 inches on average. Doesn't mean it's always going to be 2 inches, it could be 6 inches, who knows, right? But on average, given the size of my sample, I would expect it to be about 2 inches. Any randomly selected sample should be about 2 inches from the actual population mean, okay? We can also interpret this as the expected difference between the sample mean and the population mean. So again, your standard error is an estimate of precision. How precise is my measurement, right? I know that my sample isn't going to perfectly match whatever the population parameter is that I'm looking at, right? But what I do is I can calculate my standard error and start to get an estimate of how precise I should expect this to be. And if I were to conduct this study over and over and over again about how far I should expect my statistics to jump around from one replication to the next, okay? So here, in this example, our population standard deviation is 6, right? So on average, if we're looking at adult height, we're expecting a population mean of 68 inches, but on average, any randomly selected person will probably deviate about 6 inches from the mean height, right? Well, then what I do is I can take that standard deviation, divide it by the square root of 100, which is 10, and I get a standard error of the mean of 0.6, right? And so what happens is that, say I collected my sample and I've got a sample, it says instead of 68, it says the mean of my sample is 70, right? But on average, samples, I would expect my mean to be about a half an inch away from the, on average from the population parameter. I would expect about a half an inch of error between one mean to the next. So again, standard error, incredibly important. Like if you're at loss for an answer, standard error is probably a good guess, okay? It just ends up being crucial to anything that we're gonna do with inferential statistics, and we'll talk about that in a moment, okay? Questions about this? I don't know, like wake up, like back, I don't know, standard error, I just wasn't paying attention. Questions about distribution of sample means? Okay. Factors influencing your standard error. Population standard deviation, right? If we look at the formula, and this is again why you shouldn't be afraid of formulas, right? Standard error, population standard deviation over the square root of the sample, okay? Pretty simple. There's only two things that can influence it, right? You just have to look at it and say, okay, these are the things. Population standard deviation is we get more variability in the population, that increases our standard error, right? If we've got two distributions, two populations, say standard distribution, or the standard deviation of height for men, standard deviation of height for women, men have more variability in height than women do. We would expect standard error, if we're looking at the population of men, to be larger just because they have more variability than the women, okay? But really this is kind of the small potatoes. Your standard deviation of your population really isn't the big player. Big player in terms of determining your standard error is your sample size, okay? Law of large numbers within statistics says that the larger your sample is, the more likely it is that your sample means any type of characteristics of your sample are going to be closer to the population mean, right? Your samples get larger, they get more inclusive, they get more representative, and so as our sample size increase, it's going to drive down our standard error, okay? Square root of your sample size there in the denominator. As that sample size gets bigger, what happens to your denominator?
It's bigger.
Denominator gets bigger, what happens to my outcome of the fraction when my denominator gets bigger? Steph? What happens to the fraction as the denominator gets bigger? It gets smaller, right? And if standard error is going in the denominator of our test statistics, do we want lots of standard error or small standard errors? Small standard errors, right? Because that's going to make our test statistics bigger. Conceptually, that's sort of mathematically, you can just look at it that way. Conceptually, you can think of this as my sample sizes get better, my measurements get more precise. I have less static. It's going to be easier for me to detect differences, relations, as my sample size goes up. If you plot this out, for standard error, you get your standard deviation over the square root of n, right? Holding your standard deviation constant as that sample size increases, you see an exponential reduction in your standard error, okay? This is the formula at which people will say, and you'll hear this in statistics, what constitutes a large sample? 30, right? That's not a large sample. It's a modest sample for group-based stuff and experimental things. But what happens if we look at about 30, right? In terms of driving down your standard error, the addition of a larger sample starts to become, yes, less bang for your buck as this goes out, right? This will asymptotically approach 0, but we'll never get there. But you know, things start to taper off around sample sizes of 30. But big driver in your standard error is going to be how big your sample is. Okay. Questions here? All right. So distribution of sample means, if we just take a look at this in terms of IQ, just because this is a nice sort of example, we have a known mean standard deviation. So we've got 4 sampling distributions here. Sean, which one of these sampling distributions is associated with the small sample size?
The black one.
The black one. How do you know that?
The frequency is just lower.
Right. So again, this isn't the distribution of scores, this is the distribution of means that we've collected of a certain sample size. We clearly have a lot more variability in this black distribution. It's implying that, because we know standard deviation doesn't change, right? We know that this must have a much smaller sample, be associated with a much smaller n than, let's say, this blue one. This blue distribution here, very tight, not a lot of variability. We would assume that our sampling distribution associated with this blue curve associated with a much higher, much larger sample than the black distribution here. Okay. But Hee-Jung, what is the mean for all these distributions? 100, right? And so we know that with IQ, sort of standardized scores, 100 is the mean, because we made it be the mean, right? And so even though we've got differences in our sampling size and differences in our sampling distribution, the expected value of the mean across all these sampling distributions is still equal to the population mean, right? It's just our variability gets much, much larger as our sample size goes down. Questions about how all this is fitting together? Okay. So, summarize, we've got 3 distributions that we've talked to in lecture up to this point. We've got a distribution of our population of scores, right? This is the individual scores for each unit in the population. Your population of scores has its own shape, mean, and variability. We also have looked at a distribution of sample scores, right? We can't measure everybody, so we grab a sample of people, right? And our hope is that we can infer something about the population based on this sample. Distribution of our sample scores, subset of scores selected to represent the population, has its own mean, shape, and variability. Then we have our distribution of sample means, right? Distribution of sample means is made up of the sample means from all possible samples of a given size. This also has its own shape, mean, and variability. So if we look, this is our population, right? Let's say this is IQ scores, right? This is the population of scores. It's a wonderful bell-shaped curve. This is everybody in the U.S. Everything forms a nice shape here, but we can't directly observe that, right? We can't give an IQ test to every human that's residing in the country. And so what we do is maybe we grab a sample of 30 people, right? We grab this sample of 30 people, we test their IQ, we get a distribution of our sample scores. That's ugly, right? This is nice, I like that, that makes me sad. But if we look at the mean, it's not far off, right? A sample of 30 is a decent size, but it's not huge, right? We're not getting all the extremes involved. Well, it looks like we managed to capture a genius or two in the whole thing. But what we get is something that at least is kind of close, right? So we've got a mean of 102 and a standard deviation of 15.6. Our population mean is 100 and a standard deviation of 15. We actually did pretty nice. We did a nice job with that, right? But then what we do is we have our distribution of sample means, okay? This would be the distribution if we were to plot all possible means from the population of sample size 30. This is our distribution we would get here. Here, our expected value of the mean and our distribution of sample means is equal to our population mean, right? But the variability of this distribution considerably smaller, right? Variability of this distribution would be calculated as 15, because that's our population standard deviation. Divide that by the square root of our sample size. So 15 divided by the square root of 30 is going to give us 2.8, right? So what this would suggest is that the mean of all possible means of sample size 30 is still going to be 100 here, but we would expect about a 3-point difference between any randomly selected mean out of that distribution and the actual population. We would expect about a 3-point difference between any 2 randomly selected samples, or we would expect our sort of general error if we were to pull out and measure IQ with a sample of 30 to be about 3 points. People see how this all comes together, makes some sense? Okay. can kind of be tough to wrap your head around. You might have it now, you probably lose it later, but that's fine, go back through and pick it up, that's how learning happens, yeah.
Yeah, I was gonna ask you if you could repeat that whole sentence you just said. So in the population, you expect a variation of 3?
In the in the
What?
population,
I was trying to write and listen, sorry.
right? In the population, how much difference would we expect to see between individuals' scores? 15, right? That's a standard deviation of our population of scores, right? Now our distribution of sample means, this is the mean, or this is the distribution of all possible means that could be measured from samples of 30 in the population, right? And so what we would expect is, here we're looking at differences in scores. Here we're looking at the differences in means from random samples of 30 individuals. Here we would expect, all right, I go through random digit dial, grab 100 people or 30 people, measure their IQ, we get a mean. I do it again, go through, maybe I get some of the same people as I did the first time around, bring them in, measure their IQ. How much difference would I expect in those means across those two random samples on average? 2.8 points, right? So the mean of those samples of 30, I would expect to jump around by about 3 points, right? Now that's not to say that that's what it'll be. I could get a 10-point difference, right? But on average, if I were to do that again and again and again and again, on average, I would expect about a 3-point difference between each one of my means. Okay. Just think about maybe, I told some people it was very exciting. So after I give a quiz for my intro psych class, I've been teaching for what is like my 5th year or something like that. I want to go through and see what the mean on a quiz is relative to other courses or other semesters, right? So just to see if I'm doing something wrong, if something's going on, if people have a good thing, all right? And so if you were thinking about each semester as, and it's not really, but if it was a random selection of students taking approximately the same exam, right? We can think about that as starting to build a distribution of sample means. If I taught the same course and used the same test indefinitely until I'm 80, I could plot out the mean of quiz 1 for all those classes, and what I would expect there based on this is sort of the mean of individual classes to jump around by about sort of whatever the standard error would be there. And so what I had my students take quiz 1, looked at their score then, it was a 71.9, and the mean of everybody else who had ever taken that quiz, and it changes a little bit, but it was like 71.5 or something like that. It was really exciting. It's wonderful consistency. It's not a great average, it's fine average, but at least it's a consistent average, right? I know that I'm getting no better or no worse in teaching this stuff over the course of the semesters. Okay. All right. Questions on this? All right. So why is all this important? What we do and why we want to take into consideration distribution of sample means is what we want to do is find the probability of randomly selecting a sample of a certain size that has the characteristics which we observe. The question is, what is the probability of randomly selecting a sample having a mean of 1? Right? Now all of a sudden this starts to get interesting, right? This starts to become something that we might be interested in. At our very basic, it's the very basic level. We'll do this for this week, and then you'll probably do it a handful of times throughout the rest of your career. What we can do is start calculating a test statistic. We can start calculating z-scores for sample means. Same methods that we use to locate the location of individual scores. But what we're going to do here is we're going to substitute individual scores with the sample mean, right? So our test statistic for our z-test here is going to be our sample mean subtracted from some assumed population or known population value over the standard error that we need. Okay, and this is our test statistic. This is our sort of basic foundational test statistic that will then leap into our subsequent discussion of t-tests and things along those lines. Okay. When we're using z-scores, if we're using a z-test, This is in circumstances where we have a known population mean and a known population standard deviation. So why might this not come up very often in your day-to-day work? What do you think, Zach? Right. Very, very rarely do we actually know, oh, this is the mean of the population, or this is the standard deviation of the population, things along those lines. We're often working with just samples and don't have access to that stuff. But there are circumstances, and you'll notice it in these examples here. Each one of these, we're working with a situation where we know this population, we know we have some reference point in the population, and we know the standard deviation of that population. And if those are, we have access to those things, we're working with the z-scores. Okay. So, some examples, right? SAT scores form a normal distribution with a mean of 500, a standard deviation of 1, right? What's the probability of randomly selecting a sample of 10 students with an SAT score less than 440? We can do this, right? Given the information that we know and properties of the distribution of sample means, we can start to calculate this, right? We might ask, what's the likelihood of selecting a random sample of 75 students with a mean SAT score less than 440? Right? What's the range of mean values for samples of 25 that could be expected from the middle 80% of the distribution of SAT scores? So basically, we're just doing all the things that you're doing in problem set 3 right now, and we're taking those same principles and we're applying it to means as opposed to individual scores. People sort of see this process here, so we can do one of these, for example. So what's the probability of selecting a random sample of 10 students with a mean SAT less than 440, okay? So first thing we need to do is calculate our standard error, right? We know that standard error is our population standard deviation over the square root of our sample size. In this first one, we've got a sample of 10, right? This math all works out quite nicely to give us a standard error of, oh no, it doesn't, the square root of 10 is not an easy number. Someone do that math for me? What do divide by the square root of 10?
3.162.
Okay. 3.16, okay?
Well, that's the square root of 10.
Oh, whoops.
Sorry.
So what's 100 divided by 3.162?
31.6.
So 31.6. Okay, cool. All right. So then calculate our z-score, right? We want to know our sort of mean here is 440 minus 500 divided by 31.6. What do we get? Maybe 1.9. Okay, we'll call it 93.
I have
Okay.
a question. So since it says less than 440, oh, my math, I actually did 439. Would that be wrong?
Nope, 440.
Do 440?
Yep,
No,
yep.
it says less, just.
Yep,
Okay.
yep.
Okay.
Okay. So is this,
That's a 439.
okay. Someone else. It is this, you gotta be, Zach, what do
Yeah,
we got?
it's not much, but it's about negative 1.9, so negative 1.89.
1.89? Okay. 1.89, okay. So that's our test statistic, all right? So what we can do now is, how are we gonna determine the probability of selecting a random sample of 10 students with a mean SAT score of less than 440? What are we gonna go to here? Young, what do we might reference to identify the probability here? Someone say z-table? I heard z-table, okay. Someone tell me, all right, if we're looking in here, we've got this here's mean is 500, right? 1.89. This is 440. Where are we? What part of that distribution are we interested in? The smaller part, the tail, right? Okay. And so, what's the probability of randomly selecting a sample of 10 students and having the mean of that sample be less than 440? Rachel, you got that?
2.94%?
2.94? So 0.0,
Yeah,
Two
0.0294.
0.0294? So 2.9, so a little less than 3%, right? And so we can start, would we be likely to get 10 people together, randomly select 10 people, and have their mean score be below 440? No, right? And so what we would start to say is that would be a rare occurrence, right? We probably wouldn't find that, right? Now again, so here we're not working with individuals, right? We're looking at samples of 10, but if we were to collect a random sample of 10 individuals, what's the probability that they're gonna have a very, very low SAT score on average? So what is about getting close to 2 standard deviations below the mean? Pretty small, right? And so we can go through and go through the same process to find, collect a random sample of 75 students with a mean SAT of less than 440. This is the same thing, right? So if we go through and we do this again, this time instead of square root of 75, what's my standard error now? 100 divided by the square root of 75.
11.55.
11.55, okay. What happened to my standard error relative to the previous? Yeah, got a lot smaller, right? I went from a sample of 10 to 75, and my standard error jumped from 30-something down to 11, right? So literally what I would expect with a sample of 75 for my value that I find to be different from any other mean value of sample size 75 would be about 11.5 points, right? So we've increased the precision of our estimate by a great deal. So now, if we go through, take 440 minus 500, 11.55, what's my new z-score here? My new test statistic. What do you got, Seth? It died?
It's really big. Negative 5.19.
Negative 5.19, okay. Boy. Now we're way out here, right? So we're over 5 standard deviations in this tail, okay? You can't even, that's not even a value in your z-table, okay? So what happened? Why did my probability become much, infinitely smaller with a sample of 75 than with my sample of 10?
It would be even harder to get 75 students in that tiny tail.
Exactly.
Like it would be even more rare.
Right. 10 random folks can be all over the place, right? It's not likely, it's less than 3% that I would get 10 people together and find that their SAT score is less than 440. But if I get a much larger sample, if I get a sample of 75, it's me randomly sort of reaching into the jar and grabbing out the booby prize like time and time again, right? It's me getting double zeros on a roulette wheel, 50 times out of 75 spins. It's just very, very unlikely. Not to say it's impossible, but that's a very, very, very low probability event that we would do that, right? And so you start to see, as our standard error starts to increase or starts to decrease, the likelihood that some of the stuff is going to happen starts to go down quite a ways. Okay. People starting to see how this is working. So, what's the likelihood of randomly selecting a sample that's really weird? If it's a small sample, it's probably low, but not outside the realm of possibility. As I start to get very large samples, what's the likelihood that they're gonna deviate significantly from my population mean? It starts to get, increasingly close to zero. You kind of see some of the unique aspects of this piece of stuff? Okay. All right. So generally, right, what we need to do, so we got our test statistics, we're doing some stuff, what we need to do is start to interpret this, right? Two possible explanations, right? And you should always keep this in mind. There's two things that could be happening when you get your data. One, our data is caused by some systematic factor associated with a reliable relation, right? Something like that, right? There's a real effect. Like the differences that I'm seeing in my data is a consequence of a real effect. Or it's chance fluctuation, right? It's just jumping around. I just got a really weird sample and ended up with a sample of 10 individuals with the SAT score, the mean SAT of below 44. It's not gonna happen very often, but it's gonna happen on occasion, right? And this is just random fluctuations in our data. Our null hypothesis procedure, right? Our null hypothesis significant tests, our inferential statistics give us a set of procedures to try and sort of tease apart the extent to which our data may reflect reliable effects versus things that are more just a consequence of random fluctuations. Okay. So for example, what we want to do with our hypothesis test, we want to take sample data and start to draw some inferences from some unknown population value. Okay? So let's say in this example here, I have rats, and I know rats that are bred for lab, on average, they have a mean weight of 400 grams, right? Because these rats are bred to be genetically identical. You get some variation, but on average, rats bred for labs weigh about 400 grams. Right? And so what we do is then we take from this rat with a known population, we go through and we extract a sample, and we give them some sort of treatment, right? We give them growth hormone, something like that. We juice them up with some stuff. And then what we do is we go through and we measure the characteristics of that treated sample. Our question is whether or not this treated sample has the similar mean as the known population after we've gone through and done something to it, right? We've taken rats from this population and we've changed their population. They're no longer normal population rats, they're treated rats, right? But what we want to know is we can't take all the rats and beef them up and then measure their characteristics. What we can do though is we can take a sample of rats, beef them up, measure their characteristics, and then try and make some inference about this unknown population parameter of treated rats, right? And so if we assume a population has some mean of mu, what's the probability of randomly drawing a sample from that population with a mean of M or more extreme? Just like we did over here. If the probability is determined to be low, right? If it would be uncommon to sort of randomly select individuals with a set of individuals with a mean this extreme, we would typically conclude that the population from which that sample was drawn actually has a mean that's different than whatever we're testing under the null hypothesis. Okay, so in this example, if we were to find that our treated rats have a mean weight of 500 grams, right? And we went through and we took a look and let's say we had 50 rats, right? 50 rats, and we see a jump 500 grams. Never mind, I don't have variability there. That seems like a pretty big jump in weight of rats, right? Particularly if we have a mean of, or a sample of 50, right? If we went through and we calculated our test statistic and found it would be very rare to have, if the true population mean of the treated rats was 400, it would be very, very rare to get a sample with a mean value of 500, right? And so what we would start to infer then from that is that probably this population of medicated rats, we don't know what the population value is for their mean weight, but we're assuming that it's something that's not 400, right? We're assuming that it's something different, okay? So again, this is something we forget a lot. We don't think about this, and we often are focusing on our samples, right? No one cares about our samples. Like thank you sample for coming in and helping me out, but I don't care about you or your specific characteristics. What I'm interested in is testing your specific characteristics and inferring something about our population, right? Because rarely is ever the case my concern with people who come into my lab, right? Like that's not the group of individuals, and I'm not gonna write a paper and say the group of individuals who've come into my lab, that's who I'm focusing on. People are gonna say, nope, you need to look broader, Dr. Clapp, right? And so what we're trying to do is we're trying to pull people in and sort of infer something about the larger group of people based on the characteristics of this sample that we've drawn. And this is why it's so important to think about the characteristics of your sample. Is your sample good? We rarely, if ever, have an opportunity to draw a true random sample, right? And so what we have to start thinking about is, okay, the sample that I have, who's the population? Like, who does this sample represent? And then we start to use that in our interpretation of our statistics. So, example of a hypothesis test here. Researchers believe antioxidant supplements may reduce and reverse age-related cognitive decline. A sample of 25 adults aged 65 or older take antioxidant supplements for a period of 6 months. Okay? Participants are given a neurological test to assess cognitive functioning. Scores on this test are known to be normal in the population, with older adults, 65 and older, scoring a mean of 80 with a standard deviation of 20. So in this scenario, we've got, we're trying to see if antioxidant supplements increase or improve cognitive functioning. So what we do is we have a small sample, 25 older individuals come in. We have them take antioxidant supplements for a month or 6 months, and then what we want to do is see whether or not the characteristics of this sample are consistent with the known parameters of cognitive functioning in the population. Okay? So our procedure, we're going to go through a series of steps. First thing we're going to do, state the hypotheses. Okay? What we're doing with our hypotheses is we're predicting the characteristics of a to-be collected sample. Okay? We're saying sort of this to-be collected sample, because we want to state our hypotheses before we've run our analyses, because then it's a little bit tricky, right? We want to call our shots on the front end, right? And sort of make some predictions about how my sample is going to reflect a population and how those population scores are going to be different from known parameters, at least in this case. We're going to set a probability criteria for determining a reliable effect. Okay, we actually don't set this, our field sets this for the most part, but we can play around with it a little bit. We're going to collect sample data and we're going to compute relevant statistics. Not only our hypothesis tests, but also confidence intervals, effect sizes, things along those lines. And then what we're going to do is we're going to draw conclusions about the behavior of our populations of interest based on characteristics of our sample. Is this ringing bells to people? Yeah. Okay. Statement of our null hypotheses. Again, this is going to involve actually two related hypotheses. Our null hypotheses, in general, standard generic null hypotheses is there's a zero relation between the IB and DB in the population. Right? My sample will have a mean that's equal to some known population value or some value that we've specified under the null. The treatment, the manipulation, whatever we're doing has no effect on our outcome. That's essentially what we're talking about with our null hypothesis. Alternative hypotheses, some relation exists between the IB and the DB in the population. Okay, treatment has some reliable effect on outcome. Our null hypothesis testing tests only the null hypotheses. Okay, based on evidence from the sample data, we're either going to reject the null hypotheses or fail to reject the null hypotheses. Null hypothesis is only the only hypotheses of direct concern with this procedure. Okay. So, and as a preview to what, which hypotheses are we actually interested in? Okay. The alternate hypothesis, right? That's what we're actually interested in, but our procedures don't let us look at that, they only let us look at the null, and that starts to get complicated in terms of inference and things, okay? Other thing, who are we interested in identifying in these statement of our hypotheses? Are we interested in the sample, or are we interested in the population? What do you think, Judah? The population, right? And again, I will ding you on this, okay? Because when we get into t-tests and things like that, to say that the mean of sample 1 is going to be equal to the mean of sample 2 is ridiculous, right? No one cares about your sample means. And we don't need to run a hypothesis test to tell that your sample means are different. You can see sample mean here is this number, sample mean here is that number. Those two aren't the same number. So we don't need an elaborate test to go through and tell us that those two numbers are different, right? What we're interested in is the population from which this sample was drawn, is the population mean reliably different than this other population that I'm interested in comparing it to. We can't compare those two populations, but what we can do is we can grab means or samples from each one of those, test the mean of the sample and say, are these two sample means different enough given what we were expecting in terms of error, to make the assumption that they're drawn from populations having different means, okay? So when you're making your statement of your null hypotheses, always be making sure to frame this in terms of your population and not your sample, right? And also being able, and making sure to identify who your population is, right? If you just say the mean of the alternate hypothesis or the null hypothesis is that the mean of the mean of these populations are equal, I am dumb. I don't know what you mean. I don't know what populations you're talking about, right? I wrote a question about these populations, but maybe you're talking about different populations. I don't know. You tell me what populations we're looking at here, okay? And so just being very cognizant of that. If you're doing this again, it's my way of trying to force you to recognize that we're not looking at samples. Right? Samples are just our means of trying to test whether or not we have relations in the population or deemed differences across different populations, things along those lines. So, for our supplement example, our null hypothesis here is that the mean of our people taking supplements is going to be equal to this known population value of 80. So, population of older individuals using herbal supplements is going to be equal to 0. Okay. Our alternate hypotheses, population, the mean of the population of supplement users will not be 80. The population of older individuals using herbal supplements is not equal to 80. Okay. Again, pretty straightforward, easy stuff, but you notice here that I've framed both of these statements in terms of population parameters and specifically identifying what population I'm talking about. Okay. And again, this is just a nice way to start to force yourself about thinking about this stuff a little more deeply. Who are we talking about? And start to bring in some context and things along those lines. So, get our statement of population, set our decision criteria, okay? What we do is we set a probability threshold, right? We're gonna say the probability of obtaining sample of a certain characteristic, assuming that our null hypothesis is true, this is the lower bound of what I'm going to accept in terms of, yeah, this would be reasonable, versus anything beyond that. Any value less than, or any probability less than a certain value is going to be too far off, too inconsistent for me to say, yeah, it's likely that these data will, or these samples will pull from a population with mean equal to whatever our reference value is under the null hypothesis, okay? So what we do is we set that probability threshold, and if we find a sample mean to be much different from our proposed population mean, right? It's a very, very unlikely that we would randomly select a sample with these characteristics, assuming the null hypothesis is true. We interpret these data as incompatible with either A, our null hypothesis, or B, the underlying assumptions of our statistical model, right? This is where Weinstein, Greenwald, some of those papers really start to sort of criticize our standard assumption, or our standard interpretation of null hypothesis tests, in that if we get a reliable test statistic, a small p-value, we say, well, the likelihood of me obtaining these sample, assuming the null hypothesis is true, is very, very low. And so, well, you might get a low probability sample either because your null hypothesis is not compatible with what you've got, or you violated all the underlying assumptions of your statistical model and you've applied a procedure that doesn't make any sense, right? And it's not necessarily that your data are all that deviant from what would be expected under the null, it's just all of your assumptions, that you've got a representative sample, that your scores are adhering to some sort of distribution, that your variances are equal and things along those lines is all screwed up, and so that's what's driving that low probability, that low p-value. Our null hypothesis doesn't tell us which, okay? So this rolls back into our methods, making sure our methods are sound, our conceptualizations are sound, our procedures are tight, that everything makes sense, so that we can't say, oh, I rejected the null hypothesis, but it's probably because I have crappy methodology. No one wants to write that in a paper or a dissertation. Okay? If, however, we get sample means that are similar to the hypothesized mean, or are within our bounds of what we're going to call unlikely, we interpret these data as compatible with our null hypotheses. Null hypothesis tests us whether the data are unusual, but it does not apply that the model or any aspect of the model is correct. Okay. So this is very different, right? This is sort of a subtle but important point to make. Just because we fail to reject a null hypothesis doesn't say that the null hypothesis is true, okay? It just says that these data are plausible under your stated null hypotheses, but it's not saying that that specific hypothesis or that specific parameter is the parameter. Okay? So our threshold for statistical significance, determined by us, the investigator, mostly by convention, but to some degree us, instead of as our alpha level. This is a probability threshold defining our critical regions. Okay? If we find sample values that extend beyond into the tails of our distribution, falling beyond these critical regions, we're interpreting this sample as implausible. Right? It would be unlikely for me to collect a sample with these characteristics, assuming that the null hypothesis is true. So, for our supplementary example, okay, this is the distribution of all possible means of sample of size 25, assuming that the null hypothesis is true. Okay, this is our expected region. High probability values if the null hypothesis is true, right here in the body of the distribution. But we set an alpha level at 0.05, right? On a two-tailed test, what's the probability that we have in each one of these tails? Gabby, do you know?
2.5.
2.5%, right? So the likelihood of, assuming that the null hypothesis is true, the likelihood of me randomly selecting a sample of 25 individuals with a sample falling in this tail or that tail, a total of a 5% probability, 2.5 in the upper, 2.5 in the lower. Okay, questions on this, setting our critical values? Okay, what we're then going to do is calculate our test statistics. Again, as I talked about, our most basic scenario here is our z-test, right? Where we have a known population mean and known population standard deviation that allows us to calculate statistics using our z-tests here. First thing we're going to do is we're going to calculate a confidence interval around our mean, okay? Confidence interval, remember, is our mean value plus or minus our z critical. What determines our z critical? So, critical value for z, when we're calculating our confidence intervals before, what was in the last class when we were calculating confidence intervals, what determined this critical value here?
Our percent of
our percent confidence interval, right? Our precision. So if I have a 95% confidence interval, my critical value is 1.96. That's the z-score that cuts off the upper plus or minus 1.96 cuts off the upper 2.5%, the bottom 2.5%. If I decide to calculate a 99% confidence interval, my Z critical value is 2.58, right? That cuts off the top 0.5%, the bottom 0.5%, right? And then our standard error, okay? We can also calculate our informal test statistic. In this case, it's our Z-score, right? And what we can use this is use our Z-score to calculate position of the sample relative to the known population mean. So to under the null, right? This would be where this sample would fall, assuming that the null hypothesis is true. Our Z-test, as we calculated over there, is just our sample mean minus our reference mean over the standard error of the mean. Standard error of the mean is just population standard deviation divided by the square root of our sample size. Okay? Same stuff we were doing on the board over there. Questions about this? Okay. Something to note, always, and again, people will sort of ignore this because I don't know if they don't care about it or if it makes them frightened or gives them GI stuff, I'm not sure. Always go through and take a look at your test statistics. You can learn a lot of, you can sort of glean a lot from your test statistics by just looking at what goes into your test statistic, right? You can get a conceptual idea of what's going on with these ratios just by looking at this. For your Z-test, or for your Z-test here, numerator, the difference between our sample data and our null hypothesis, right? So how far did our sample fall from our expected value under the null hypothesis? It's a deviation score, right? It's just how much different is it? Our denominator contains the expected difference between a sample mean and the population mean under the null hypothesis. Remember, that's what our standard error is. Our standard error is, on average, if I select a random sample of this size, how far would I expect that to fall from the population mean? And so we can see here, we start to see our Z-test and most of our test statistics that we're going to be working with this semester as a ratio of what we got over what we would expect just given sort of random error in our data, right? So if our, the deviation we found from the mean is about the same deviation we would expect just based on what we would get of a sample this size across replications, we're going to get a Z-test that's sort of at 1 or probably lower, right? And we're probably going to say, well, that looks like it's about what we would expect given sort of the variability that you see. But if we get a deviation score, if our sample mean falls a great distance from our assumed value under the null, and that distance is much larger than what we would expect just due to random chance, our Z statistic, our test statistic is going to be quite large, right? And that's when we start being able to reject our null hypothesis, claim statistical significance, reliable differences, reliable associations, things along those lines, okay? So if you're looking at this, think about, this is my signal, this is my noise. Like, how much static do I expect to get? If my, what I saw in the data is about what I would expect based on general static across replications, I'm probably going to say, yeah, this is just sort of about what we would expect, right? But as soon as my observation starts to far exceed what I would expect due to just random variation, that's when I start to get a little more confident that I've got a decent signal going on there. Okay. Questions about this? So again, don't just use this for the purpose of calculation. Look at it, think about what it actually means. It will add a great deal of meaning into your inference and things along those lines. Okay. So we're going to run a couple scenarios here. Scenario 1, what is the disease statistic if individual is taking antioxidant supplements? Again, our sample is 25. Scored an average of 92 points on our neuro assessment, assuming a mean and population of 80 and a standard deviation of 20. What is our Z statistic for individuals, older individuals taking antioxidant supplements if they score an average of 84 on that assessment? Okay, let's take a break. We'll go through and work through these. So, 1 and 2. Play around with a couple of these hypotheses tests here. So, first scenario, we want to take a look at probability or sort of run our hypotheses test for individuals. Let's say we got a mean score from the individuals taking this supplement. We got a mean score of 92. Okay, and so our null hypotheses, remember, is that mean of supplement is equal to 80. Our alternate hypothesis, mean supplement not equal to 80. Okay? And this is a non-directional test. This is a two-tailed test, right? So we're saying, and the Howell chapter talks about this a little bit, right? We're saying that it's possible that these supplements make people better. It's also possible these supplements make people worse, right? We don't want to fail to reject the null hypotheses if it's in the opposite direction we put all of our critical region on one tail, right? So we're looking at either way. So we're just saying that the mean of the population of older individuals taking antioxidant supplements is some value that's above or below 80, okay? So, first scenario here. What's the first thing? So we've got samples 25. Our mean under the null hypothesis is 80. This is our sort of what we know the population of older individuals score on this neuropsych exam, and then we've got a standard deviation of 20. Okay. What's the first thing we need to do? What do you think, Sean?
Find out, we have to take the square root of the number of people in
Right. We need to calculate a standard error, right? Standard error is going to be central to any of this stuff that we're doing. So we've got our standard error of the mean here is going to be our population standard deviation over the square root of our sample size, which is 25, gives us 5, a standard error of 4. Okay? So essentially, like literally what we're saying here is we expect that on average, we're going to be off about 4 points in terms of our error. Any two randomly selected samples of individuals from the population are going to be, on average, about 4 points apart. We would expect any average sample to be drawn from the population of older adults on this score to be about 4, well, sample size 25 to be about 4 points from the mean on average, right? So this is our static. This is the random variation that we would expect just based on the fact that we don't have access to the population, okay? So the first thing, the very first thing, this is gonna be this is a change of sort of deal. Before you calculate your test statistic, I want you to calculate a confidence interval, all right? As you're going through this semester and working on things, your test statistic should be the last thing that you calculate. The first thing you should be doing is calculating things like confidence intervals and effect sizes and things like that. We're going to make a big push this year. I've always had a big push with effect sizes and confidence intervals. Effect sizes more, confidence intervals more recently. But oftentimes what happens is these end up being sort of like an add-on. We run our null hypothesis test. We say we reject, we fail to reject, and also here's a confidence interval. That ends today. Okay. No more. I'm saying no more of that. Right. The first thing you will calculate is a confidence interval. Make a substantive interpretation of that confidence interval within the context of your problem, and then by the end of it, we can say, and also we find evidence for a statistically reliable effect, things along those lines. Okay. So, but for this, it's easy. We want to calculate 95% confidence interval, right? And that's just going to be our mean that we got here, mean of 92. Okay, we got our mean 92 plus or minus our critical value. What's our critical value going to be, Rachel?
1.96.
Excellent. 1.96. Okay, times our standard error is 4. Going to give us a confidence interval 84.2 to 99.8. Okay. Who's brave? Someone give me an interpretation of this confidence interval.
Doing an infinite number of random samples, 5% of those would have, means that are outside that range.
Okay. And this is the tricky part when we start talking, when we start using the statistical definition of the statistical interpretation of a confidence interval for our individual interview, right? Again, because remember, our confidence interval is about, our confidence level is about the process of calculating intervals, right? And so from a statistical standpoint, we would say that over an infinite number of replications, 95% of the intervals collected across those replications would be expected to capture the true population parameter, right? Now, is this one of those 95%? I don't know, right? It's just one. I can't say a whole lot with that, right? And so what we can start to do is start using this as an estimate of our level of precision and range of values that are within, so that are compatible with our data, right? So we might say, so based on these data, the mean value of, the mean cognitive scores for older adults taking antioxidant supplements was 92. These data suggest that plausible values for the true population mean fall somewhere between 84 and 100, right? So we're looking at the precision of our estimate. We all might also say sort of our margin of error here is plus or minus 7.8, okay? How did I calculate that margin of error?
The 1.96 times your
Right.
standard error.
Okay, so I could say, based on these sort of my, we could say my point estimate of cognitive functioning for the population of individuals, older individuals taking antioxidant supplements, based on these data is 92 with an expected error of about plus or minus 8 points. We could also say that values of around 84 or 100 represent, based on these data, reasonable lower and upper bound estimates for the population, for mean cognitive functioning in this population. We could say that values falling, values for mean cognitive functioning falling between 82 or 99.8 are consistent with these, would be considered consistent with the data that we've collected in this study, things along those lines, right? So what we're doing with this confidence interval is we're getting a sense for not just what our point estimate is, which is fine, right? And if you had to put a gun to my head and say, what's the mean cognitive score for this population of individuals, I'd still say 92, right? But here I can see we've got about an 8-point swing above or below. That's not terrible, but it's not super precise, right? There's a lot of flux going on there. We could also, if we wanted to, and we haven't done this yet, but we could also calculate an effect size, right? We could calculate, so we've got our score, 92 minus that assumed under the mean, under the null, is 80, over our standard deviation is 20, gives me an effect size of about 0.67. And I could use that and I could interpret that. That's consistent with a medium effect, right? What I would, how I would interpret that, I would say older individuals taking antioxidant supplements in this study scored about 0.6 of a standard deviation above the expected value in the population more generally, right? That's not trivial, right? So these people we went through, and they were of this population, and we took them, and using science, we made them part of this population, and sort of their mean cognitive functioning now is estimated to be about 0.6 of a standard deviation above sort of what we would expect from the larger population of older individuals, right? And so this is how we're talking about effect sizes. So we could do both of these, go through and make interpretations there. And then after we've done all that, then fine, now let's get to our null hypothesis testing, right? Here, we would go through and want to calculate our Z test, right? So don't get confused here. You're going to get two different Z scores. You're going to get your Z critical, right? That's your critical threshold, and then you're going to get your test statistic. Test statistic is again just gonna be the value we got minus the value we expected over the null over our standard error, the mean, right? So again, thinking about this, this is what we observed. This is actually the difference that we saw relative to our reference population. This is about how much a difference we would expect just due to random variation, right? This is how much we would expect due to just general static. And if we go through and we calculate this out, we get a test statistic of 3. How are we feeling about this test statistic of 3? Relative to our Z critical equal 1.96. Based on, assuming the null, assuming the population, the true population of, or the true population, or the true average cognitive functioning of population of older individuals who are taking antioxidant supplements, assuming their true value is actually 80, the same as the general population, is it very likely or unlikely that I would get a sample of 25 individuals with a mean score of 92? Very, very unlikely, right? And so we could go through and we could actually calculate a probability value. Someone pull up their Z-score. Tell me what the probability of obtaining a score of 92 or greater based on a sample of 25 using that Z-score. What's my probability value? 0.00 what? 13. Okay. That's not very common, right? So the likelihood of me if the true population value is actually 80, the likelihood of me randomly selecting a sample of 25 individuals having a mean cognitive functioning score of 92 is about 0.1%. Very, very unlikely, right? And so what we would do, would we reject the null hypothesis or fail to reject the null hypothesis? Zach? We would reject the null hypothesis, right? Now, so we did all of this stuff. Did we need to do all this stuff?
Yes.
Well, with the problem, yes, we did. But what did we need to do this business to know that we were going to reject the null hypothesis? Why not, Candace?
Because the probability, you can figure out the probability, so that's what people use to determine whether you reject.
Okay, so, yeah, to go through and get probability, things like that, but if we just wanted to know whether or not we're gonna reject or fail to reject the null hypotheses, did we need to do all this? Zach, you're saying no, why not?
Well, we could just look at our,
Yeah, we just look at the confidence interval, right? Is 80 in there? Nope, right? So this is a range of plausible values for the population, the average cognitive functioning in the population of individuals taking antioxidant supplements. We're saying that regional values and values that are consistent with these data range from about 84 to about 100, right? Is 80 in that confidence interval? Nope, it's outside. By definition, we know that we're going to reject the null hypotheses when we got here, right? And so this is why, and so this is not new information. We're using all the same figures. This is just sort of taking the same ingredients and baking a slightly different cake, one that's less interesting and easier to use, right? We have everything we need to know. Now we get a p-value with this, right? We don't get a p-value, but if we're just going to say, are we going to reject or fail to reject, we can see that here. We also get actual estimates for regional values for the population or the parameter of interest. We get an index of our precision. All the stuff that we get from down here that's sort of most useful, we've already gotten here, right? We get a standardized metric of our effect. We're expecting individuals, older individuals who are taking antioxidant supplements for 6 months to score about 0.6 of a standard deviation above the general population. We got all our interesting stuff here, and even some of the uninteresting stuff. The only thing we got with the the hypothesis test is p-value. Okay. And so this is something to be thinking about in terms of going through, making interpretations, things along those lines. Questions about any of this? All right. Let's change it up a little bit, do this other example just for purposes of interpretation. All right, so here we've got a mean 84, right? So our standard error is going to be 20 over square root of 25. Still gives us a standard error of 4, right? That didn't change. But what did change is our 95% confidence interval. This is now our mean, 84 plus or minus 1.96 times 4 gives us a confidence interval of 76.2 to 91.8. Before we go any farther, Steph, what can we already know based on that confidence interval that we've calculated? That our reference mean falls in it. And so what does that tell us we'll eventually do? It's like knowing the damn future.
It'll tell us, our mean goals in the range, so.
And so will we reject or fail to reject? We'll fail to reject, right? We already got that, right? So the big thing we're all interested in knowing, right? Like we're waiting with bated breath what the outcome is. We already know it, right? Because we just calculated that confidence interval, right? We'll get a p-value if we really are really hard up to have a p-value. But at the end of the day, we know based on this confidence interval that the mean value, the mean functioning score in the population of older individuals is a reasonable value based on sort of the data that we've collected from this sample, right? So our population, we know that our population of older individuals who are taking antioxidant supplements, we don't know precisely what their mean cognitive functioning score. Our best guess is 84, but given our error of estimation, we're expecting that the population of, or the mean functioning of the just general population is not incompatible with the data that we've found, right? So we can't say, we already know just based on our calculation of our confidence interval that we can't say that we're not going to be able to have enough evidence to claim that the people who are taking antioxidant supplements are any different than those that aren't taking antioxidant supplements. Okay. We calculate our effect size here. Here we've got 84 minus 80 over 20 gives us a D of 0.2, right? So we would say our individuals who are taking antioxidant supplements are scoring about 0.2 of a standard deviation above the memory score expected from the population of older adults in general, right? I mean, it's not 0, but it's not huge, right? That if our benchmark for a small effect, if we're looking at these as 0.3, we've failed to achieve criteria for what we would typically call even a small effect, right? So depending on what we're talking about here, right, it may not be trivial, right? But here we're seeing that the magnitude of our effect is quite small. Calculate our Z statistic, 84 minus 80 over 4 gives us a Z statistic of 1, right? Someone tell me what the probability of obtaining, randomly selecting a sample of 25 with a score of 84 is going to be. 84 or greater. You got this one, Rachel?
0.8413 or.
So a score of 84 or greater. So what's the likelihood of me obtaining a sample with a mean of this value or more extreme?
Oh, 0.1587.
0.1587. So not terribly likely, but certainly not something that falls within our critical region, right? Set at 2.5 on either sides of the distribution. So here we found a difference that here in the scenario 1, our observed deviation from our expected value under the null hypothesis was large enough and exceeded our expected error by enough for us to reject the null hypothesis and say, yeah, it looks like these, we probably conclude that these antioxidant supplements are probably doing something, right? Scenario 2, we still found an increase, but that increase wasn't sufficiently higher than what we would expect based on our margin of error. Actually, it was exactly our margin of error. So basically, what we found in scenario 2 was exactly what we would expect to find across random replications, and so we would reject the, or fail to reject the null hypothesis and say that we just don't have enough evidence to make a determination on whether or not antioxidant supplements increase or decrease cognitive functioning in a sample of older adults. Now, Gabby, what happens instead of a sample of 25, I have a sample of 250? What happens to my standard error?
It decreases.
It decreases by a lot. And if my standard error decreases by a lot, what happens to my test statistic? Does it go up or down? So as our standard error gets smaller, what happens to our test statistic in that in this ratio? So this number becomes smaller, what happens to this number? Becomes larger, right? So you get a much larger test statistic. So if I collected a sample of 250 individuals as opposed to 225 individuals, am I going to, also what happens to the precision of my estimate? Does my confidence interval get smaller or larger? Smaller, right? And am I likely to reject the null hypothesis with a sample of 250? You're smiling, Sean. What are you smiling about?
I don't know if you will or not. Depends on what you do with the problem.
Yeah, no, it will. It will. If I collect a sample of 250, my standard error now becomes, what's 20 divided by the square root of 250?
Yeah, 1.26.
1.26, and if I take instead of standard error of 4, standard error of 1.26, what's 4 divided by 1.26? 3.17, okay. Now all of a sudden I've got a z-score of 3. Is that going to fall outside of our, yeah, okay. So this is one of the reasons it's problematic with testing. With a sample of 250, what's my effect size? Does my effect size change? No. Right? Effect size is still, so my, the difference that I find, I still see a 4-point difference. Standard deviation is still 20, right? So I still have an effect. I still have something that doesn't quite reach standards for a small effect. But because I've cranked my sample size up, all of a sudden I've gotten a test statistic that's statistically that we are failing to reject. Now all of a sudden we very clearly will reject, right? And the only thing that changed was the number of people I had in my sample, okay? This is one of these things and sort of the paradox of hypothesis testing. We put so much effort into this, right? But the only difference between finding a small effect is reliable or not reliable is going to be your sample size. If I just keep adding people on here, eventually I'm going to push this in and it's going to say, yep, that's not 0. Yep, this sort of confidence interval, your level of precision has gotten down, so we've pushed sort of your reference value outside of that interval estimate, right? And so this is one of the primary criticisms is if this is all we have to do is just collect more people, what's the point, right? And so, but it's important to know when you're sort of looking at your own research and your null effects, right? I've got a correlation of 0.4 between X and Y, but I've only got 20 people in my study, and that correlation of 0.4 isn't statistically reliable. Do I stop collecting data on those two things and say, well, that's nothing there, right? No, right? Correlation of 0.4 is, I mean, that's you sort of getting close to a large effect right there, right? You just don't have enough people to sort of push that into the range of statistical reliability based on our standards, right? So wanting to know sort of how the sausage is made, what's going on behind the scenes, right? So that you can make sort of reasonable interpretations, so you're not sort of poo-pooing things that are clearly sort of there to be found. Right? So our supplement scenario, in the first case, alpha level 0.05, critical values 1.96, 95% confidence intervals here. Our z-score of 3 is way out on the end. We would say this is falling in the critical region. We would reject the null hypotheses. Scenario 2, same alpha level, same critical values. This time, though, my confidence interval contains my reference value of 80. Our z-score is 1. It's falling within the body of the distribution, and so we would fail to reject the null hypothesis here. So what we need to do now, draw meaningful conclusions about possible population values, the precision of our point estimate, the size of an effect based on our confidence intervals. Later we'll get into effect sizes. I'm not going to go into calculating effect sizes, but this is just kind of a preview of what that's going to look like. When we reject the null hypotheses, we make this decision when our sample statistics fall within our critical region, right? It's out there in the tails. We're suggesting that our sample data are unlikely, assuming that the null hypothesis is true, and all corresponding assumptions of our statistical model, right? This is a big assumption. I can tell you right now, we always violate that almost every time we go out and do stuff, right? And so it just lets you know how tenuous this our hypotheses tests are. Because we found that our reference value is not a plausible value within our confidence interval, that it's very unlikely that if this were the true population value for this, or the true mean value for this population, that it would be very unlikely that we would obtain such a sample or observe such a data. We then conclude that it's likely that our sample was drawn from a population with a mean having something other than what was specified under the null hypothesis. Okay? We interpret this as then indirect support for our alternate hypothesis. In other cases, we'll fail to reject the null hypotheses. We make this decision when our test statistic falls in the body of the distribution, suggests that our sample data are plausible based on our null hypotheses. Okay? We conclude then that there's insufficient evidence to claim an effect. All right, and this is very agnostic versus atheist. We don't say there is no effect. Right? We don't say that X is not related to Y. We don't say that sample A does not differ from sample B. Right? We just say that we don't have enough evidence to suggest that they do. Okay? Failing to reject does not prove there is no effect. It's just saying that we don't have sufficient data to say that there is an effect. Okay? Seems backwards, but we make this example or this mistake all the time. Never use the unfortunate phrase, accept the null hypotheses, right? You'll probably do it at some, maybe you will not say you'll accept the null hypotheses. I got called out on a paper though. I had some people, we had to exclude some people. I was just running some basic stuff and I was like, oh, okay, we didn't find reliable differences between sort of people who were in the sample and those who were excluded. And so, so there was no differences in terms of gender, initial scores on X, Y, and Z. I got called out by a reviewer. He's like, can't say there's no differences just because you failed to reject the null hypothesis, particularly when there's, 5 people who got excluded and, 100 people in the sample. I was like, you're right. I should not say that, right? So we revised that language to say we found no evidence of those reliable difference from individuals who were included versus excluded based on X, Y, and Z. That's acceptable, right? We don't have enough evidence to say that these individuals are different. And sometimes what I want to do, if I'm feeling frisky, we'll go through and say, sort of we also calculated the sort of effect sizes for differences across these variables, failed to reach standard benchmarks for a small effect, right? So it's not that we didn't detect a reliable difference because we just didn't have many people that we excluded. If we go through and calculate effect sizes, so the actual magnitude of the differences looks to be very small, right? If there were large ones in there, I might not sort of throw that out there. So we didn't detect a reliable difference, although the effect sizes were quite large. So I'm not trying to sort of actively help prevent people from publishing my stuff, but sort of knowing exactly what's going on and thinking about how can I make the best argument possible based on the data that I have. So, conclusions. I went through last time about restructuring all this to really make sure that we're incorporating effect sizes, confidence intervals as the primary sort of mode of interpretation here. So in a scenario 1, this is an example. This is not a template. Don't sort of take this, copy this, and use it as your own and just plug in different values. Sort of use this as an idea for the types of things that I would be really excited to see in your assignments, but don't, and we've had problems with this in the past, if I wrote it, if it's on my slide, it's for you to use as a resource, but not for you to have as your own, okay? So just watch out. Use some of the same stuff, be like, oh, this is, you know, how I might talk about this, or I can change this around. I don't have sole proprietary ownership of different combinations of words and things like that. Just make sure that your interpretations are coming out of your own head and not stuff from slides. But something, an example of a way you might incorporate effect sizes, confidence intervals in this scenario. A point estimate for the mean cognitive functioning in the population of older adults taking antioxidant supplements was 92. 95% confidence interval for these data suggests that values of 84.2 and 99.8 are reasonable lower and upper bound estimates for the mean cognitive functioning in this population. The probability of randomly selecting a sample of 25 with an average functioning score of 92 or greater, assuming a true population value of 80, is 0.0013. This score falls within the critical region set by alpha equal 0.05 to reject the null hypothesis and conclude that antioxidant supplements are associated with a statistically reliable increase in cognitive functioning on the other end. Right? So we're going through talking about consistently referencing the population of interest, tying in, sort of starting out with our interval estimate and sort of making some observations there, finishing up with our hypothesis test and saying these data, based on these data, we're able to reject the null hypotheses and say that antioxidant supplements are associated with statistically reliable increase in cognitive functioning among the elderly, which would be attempted to do, like we reject the null hypotheses and then leave it at that. Well, again, I'm a dummy, I don't know what that means, right? You have to tell me what that means or what it means to you. Tell me what it means to you and then I'll see if you have a sort of good grasp on what's going on, right? So this is the same thing. You don't want to just say, oh, there's an effect. And you don't want to say, oh, there's a difference, or these groups were different, because I don't know what that means. There's a couple different ways things could be different. You've got to tell me how they're different and what it means. Same thing, you don't want to just say, oh, there's a relation between X and Y. What does that look like? What does it mean within the context of the larger problem? Okay. Questions about sort of this interpretation as an example? And again, go back through that, the slides on confidence intervals. There's a lot of different ways you can go through and interpret those, right? What I don't want you to do, which is off limits for the purpose of this class, is say we're 95% confident that sort of X or Y or something like that, right? Or that this sort of captures the true population mean. That's off limits, I don't want to see it. You got a lot of other different options. You can talk about over an infinite number of applications. I would prefer you not, because that doesn't have a lot of actual interpretive conceptual meaning, right? That's basically saying over an infinite number of replications, 95% of our intervals will likely capture the mean value. I don't know if this is one of them, but just FYI, that's kind of what's going on. That's not a helpful way to interpret things. So go back to, take a look, and start to incorporate those meaningfully into your interpretations. Scenario 2, and again, this is another thing. I'm going to strongly encourage you guys, you all to change up your interpretations a little bit. What happens in addition to confidence intervals being tacked on as sort of an afterthought is that we've got our stock phrasing and then it's a cut and paste and just not actually using this interval estimate as a way to actually try and infer something from the data, right? So not saying that you can't. My strong preference though would for you to be work with different ways of talking about this, work with different interpretations to try and bring some meaning into this. So here, a little bit different scenario, right? We failed to reject the null, hypotheses. An example might be something along the lines of supplement use in older adults associated with an incremental increase in mean cognitive functioning. Give the mean here relative to the scores from the general population. However, confidence interval for this point estimate evidence considerable margin of error with deviation from the population mean failing to reach benchmarks for a small effect, right? Probability of randomly selecting a sample with a mean cognitive functioning score of 84 or greater, assuming a population value of 80 is 0.1587. Score falls outside the critical region set by alpha equal 0.05. That's kind of ambiguous, you could say, within the body of the distribution. We fail to reject the null hypothesis given insufficient evidence to claim a reliable effect of antioxidant supplements on cognitive functioning in the elderly. Okay. So a little bit different. So we still took that confidence interval, interpreted, used the margin of error to sort of provide some context around. So yeah, we did see an increased, a greater point estimate, but there was a lot of error around that. Sort of our effect size failed to reach standards for small effect, running into our hypothesis test, and so we're essentially saying we failed to reject the null hypotheses. But still trying to incorporate that information in there in terms of how you're talking about things. Questions? It's a reasonable example. It gives, kind of give you a headspace for the types of things I'd like to see in terms of your interpretations of some of these tests. Cool. All right. Do one more example here just to help solidify this for people. Again, we're still working with supplements, right? In this scenario, we've got people taking ginkgo biloba and ginseng, but it's not, it's just general people, not older adults. What we've got is we've got a sample of 36 people taking daily herbal supplements for 90 days, standardized memory test, population in the general, or scores in the general population, normally distributed, mu of 8 or mu of 80 again, but this time we've got a variance or a standard deviation of 18. Okay, and what we have is a mean of 84. Okay, so going down through, in a sense, state the null hypothesis being tested. Gabby, can you tell me what the null hypothesis being tested here is in words?
That herbal remedies, okay, so ginkgo, ginkgo biloba and ginseng won't have there won't be a difference in the effect of what you're talking about,
Okay.
of
Yeah.
memory.
Yeah. One of the things I actually like to do is to go through and sort of second question, state the null and alternative hypothesis in statistical notation. That sometimes helps put words into this, right? So, 1 and 2, right? So we've got our null hypothesis in statistical notation is that mean of supplements is going to be equal to 80. Alternate hypotheses, mean of supplements, not 80. And so putting this into words, you do a great job of trying to incorporate some of the population, things like that. I mean, it doesn't have to, like, as long as I get a sense for that you're recognizing sort of the population that we're working with, you could say something along the lines of the average memory score in the population of individuals using herbal supplements is equal to 80, right? Something like that, right? And that's pretty easy to go through and just take a look at after you've written this out in statistical notation and just say, okay, this is kind of what we're looking at here, right? But again, making sure that you're referencing the population, right? And using population notation here, right? Don't say mean equals 80, right? You don't expect the mean to be equal to 80. The mean is probably going to be some score that's not exactly 80, so that's not a useful thing to say, right? What I'm saying is that I'm hypothesizing that the population from which this sample was drawn has a mean memory score of 80. Calculate 99% confidence interval for mean memory score in the population of individuals using ginkgo biloba. So here, first thing we need to do, calculate our standard error, is gonna be 18 over the square root of 36. That gives us the standard error, 3.0. And so here we're gonna take our mean of 84 plus or minus. Now what's our interval estimate? What's our precision we're calculating here? Please, John?
1.96.
Okay. What, it would be 1.96 if we were running 95% confidence interval. What type of confidence interval did I ask you to calculate here? 99, right? And so then what would our critical value be?
2.52.
Yep, 2.58. So 2.58 times our standard error, 3.0, gives us an interval estimate of 76.3, 91.7. Okay. What do we know already at this stage of the game? Judah?
We're not gonna be able to, reject the null hypothesis.
Yeah, probably not. What's the only caveat that we might take? What's the only thing that might save us in this situation? Anybody?
Big sample size?
Our sample size is a little bit bigger, but this is taking into account the sample size, right?
Mm-hmm.
Take a look at the question. What am I asking you to do for the hypothesis test? What do you see, Trent?
Yeah, you're asking at 0.05, so basically 95%. So
Okay, right. So I'm asking you to test the hypothesis at alpha equal 0.05. Your confidence interval was calculated at alpha 0.01, right? And so it's possible that we're sort of giving you a little more leeway. It's possible that if we go through and we calculate this at alpha 0.05, we correspond to a confidence interval, a 95% confidence interval, that maybe we just eke out and are able to reject, right? But so something to make sure that you're taking a look, making sure that you're getting the right alpha, the right confidence interval estimate, things along those lines. Okay. So we've got that, and then if we calculate our D, okay, that's going to be 4 over 3, no, over 3, 4 over 18. It's going to give us a not terribly so. Okay. Then what we're going to do, conduct a hypothesis test at alpha 0.05, provide a conclusion. So our Z test is going to equal 84 minus 80 over my standard error is now 3. Gives me a Z 1.33. And so 70, are we going to reject or fail to reject the null hypothesis here?
Let's see, fail to reject, it's not very hard.
What's our Z critical here? Zach? So it's easy to see, right? Our Z score of 1.33 falls within the body of our distribution. It doesn't exceed our benchmark, our critical benchmark of 1.96. So even at alpha level equal 0.05, we're not as stringent as we were before, but we're still not going to be able to reject the null hypothesis, right? So again, we would be in a situation where we would fail to reject the null hypothesis and say that we don't have sufficient evidence to conclude a reliable effect of herbal supplements on cognitive performance in the general population. Right? There is essentially, we're saying we don't know if it hurts or helps. We just don't have enough evidence to say. Right? These data, based on these data, it looks like maybe there's a small incremental benefit, right? But based on the sample size that we have, we can't claim a reliable effect. So, and then in your appropriate conclusion, would want you to do the same thing as we've had before, right? Talk about your confidence interval. And again, I'm going to tell you, start out talking about your confidence interval. Tell me about the precision of your estimate. Tell me about reasonable values based on these data for the probable values in the population, right? Talk about your margin of error. Talk about down the road, we'll talk about effect sizes. After you do all that, then we can start talking about hypothesis testing and p-values. But by that time, I'll already know sort of what you're going to tell me, right? Assuming that our confidence intervals and our hypothesis tests are conducted at the same alpha level. So, but wanting the focus to be on sort of using some of these interpretations flexibly to sort of infer something about the behavior of the population of interest. Questions on any of this? Awesome. How are you guys feeling? There's a lot of information, a lot of stuff coming in. Luckily, a lot of this should be overlap with undergraduate statistics courses. Again, it's sort of very basic stuff, but I want you guys to understand sort of not only what we're doing, but why we're doing it. We're not just cranking out numbers because it's fun to do on a Friday afternoon, but wanting you to sort of get an understanding of what these mean and how you can start to play around with these to start to make interpretations on your data. Okay, a couple types of error. Type 1 error, this occurs when we reject a null hypothesis when the null hypothesis is true. Right? We're saying there is an effect when there actually isn't an effect. Okay? This is our most feared type of error, for better or for worse. Sort of basically, what we want to do is we want to associate our type 1 error with a very small chance, right? When we make this type 1 error, sort of in theory it should be, I just happen to get a really rare sample, right? I found, in the world of Pokemons, I found a very rare Pokemon, and so I shouldn't have found it, but I did, and I'm saying that I'm a good Pokemon finder when I just happen to run across it on accident, right? That's what's going on with our type 1 error. We want to try and minimize that. Our type 1 error set by our alpha level, okay? Alpha 0.05. We reject when the probability of obtaining the data, assuming the null hypothesis is true, less than 5% of the time, right? 1 chance. Alpha 0.01, we reject when the probability of obtaining data, assuming the null hypothesis is true, is less than 1%, right? So we're going through and starting to make things increasingly rare that we would accidentally collect a sample with these characteristics, assuming the null hypothesis is true, assuming there is no difference, assuming that the actual mean of our population is whatever our reference point is, it would be increasingly rare for us to actually grab a sample of size n that would be at or farther out than our test statistic. Okay. Thresholds for our type 1 error, and this again is for our two-tailed tests. Alpha 0.05, z-scores of plus or minus 1.96. Alpha 0.01, plus or minus 2.58, 0.001, z plus or minus 3.29. Okay. These will start to become sort of ingrained in your system as you do these more and more, and then when we get into next semester looking at regression stuff and outlier, and even this semester screening for outliers, sort of wanting to use some of these values as our benchmarks for determining extreme values, outliers, things along those lines. Type 2 error, this is when we fail to reject the null hypothesis when the null hypothesis is actually false. Okay, we conclude that we don't have enough evidence for an effect or a difference in the population when there actually is one. Okay? This is our missed opportunities. Most commonly associated with studies with insufficient power, right? If so, there is an effect, right? There's actually an effect. Like objectively, out there in the universe, this population is different than this population, right? But maybe it's a very small difference. Maybe it's associated with a small effect, and I gather a sample of 20, right? It's not guaranteed that I'm going to detect that effect, but my power is very, very low, right? The chances of me with a sample of 20 detecting this small effect are very, very low, right? Probably less than a coin flip. And so what I'm likely to do here is make a type 2 error. I'm going to fail to reject the null hypothesis, even though out there in the universe there is actually an effect there to be found. Okay. So I'm looking at the correlation between heart attacks, fatal heart attacks, and taking baby aspirin, right? In the population, that's actually a very, very, very slight effect, right? It's real, but it's very, very small, right? And so if I just have a random sample of, 50 individuals, I'm probably not gonna find that relationship, right? That's not to say that it's not there, it's just I don't have sufficient power to detect that relation. And so probably what's gonna happen is I'm gonna make a type 2 error and say that I don't have enough evidence to claim an effect when that effect actually is out there in the universe, okay? Type 2, greatest error in cases where a treatment of manipulation has a small but reliable effect, okay? Whatever I'm doing in my experiment does have an effect, right? If I ask people to do this, it does cause increases or reductions in anger, or it does increase or decrease the likelihood a jury finds a defendant guilty, or it does increase or decrease the likelihood that someone will or won't purchase this product, right? It's there, but it's just small, it's subtle, and if I don't have enough power in my analyses to detect it, I'm probably going to miss it. So things like poor, small sample size, poor measurement, right? If my measurements have a lot of error, right? If I have a really horrible estimate of whether or not people are actually going to buy this, or I have a terrible estimator of someone's, sort of whatever my outcome variable is. Outside error, these are things like your RAs aren't trained well and are screwing things up, or they're doing sort of work on the wall inside your lab and people are banging stuff around, right? Outside stuff, people don't enter data reliably, right? So people are kind of making stuff up as they go along, not coding things reliably. These are all things that can start to increase the static in your study, start to jack up your opportunities for a type 2 error. So in general, our little 2x2 contingency table here, there is no effect, the null hypothesis is true, and I reject the null hypothesis, I made a type 1 error. This is one that we fear the most, right? We don't want people getting off easy and being able to claim things that aren't there. So we're worried about this type 1 error. If an effect exists, the null hypothesis is false, and I fail to reject the null hypothesis, I've made a type 2 error. Here on the other diagonal, we have our correct responses. Okay? So important, right? Our power is the biggest thing that so when we go through and look at power in psychological studies, they're horrible. Like average power of your average psychological study is about 0.5. Basically meaning that it's kind of a coin flip whether or not you're going to detect the effect that you're trying to detect, right? That's bad news. Usually what we're trying to work for is power equal to about 0.8, right? The reason we're not trying to achieve power of power of 1 is while we have problems with underpowered studies, and that's probably our biggest concern, overpowered studies also problematic. Why might overpowered studies be problematic? Yeah.
You can find correlations or columns that don't make any sense. Like, you have a sample of 1,000, but you, for whatever reason, took down the color of every participant's shirt. You can make a correlation between being 40 years old and having a red shirt. That doesn't necessarily mean that causes you to be 40 years old. It's just
right.
You can make like irrelevant links from one thing to another.
Right. Yeah. And so maybe with big epi studies, right, where we've got thousands and thousands of people, I find that there's a relationship between walking on Sundays and brain cancer, and that correlation is 0.02, but with 10,000 people, that's a statistically reliable, at p less than 0.05, right? At a large enough sample, everything's going to be related to everything, right? And what can happen is we start drawing misleading inferences in terms of identifying relations that either aren't there or are too small to be relevant, right? And this is one of the criticisms of null hypothesis testing. We talk about, oh, this is a significant effect. What's a statistically significant effect based on our standards? But whether it's a practically significant effect, that's another matter altogether, right? And so also have to be concerned with studies that have lots and lots of people making sure that we're not reading too much into every single effect that comes up, because everything's gonna be related to everything, and you're gonna have a lot of stuff to talk about there. Okay. Questions on our different types of error? All right, now my favorite part of the lecture. Is this a reasonable procedure? We've gone through, we've talked about it, we've said, so is this something that, this is what we do and this is what we've always done? Hugely, hugely, hugely criticized for years, decades people have been talking about some of the problems with null hypothesis testing. Some of my favorite quotes from some of our readings, null hypothesis significance testing described as a potential but sterile intellectual rake who leaves in his married path a long train of ravished maidens, but no visible scientific offspring, right? We're just going through, we're doing stuff, we're claiming significance, but we're actually not doing anything. We're not moving the science forward because we're not using this technique, or we're misusing the technique. This naked emperor has been shamelessly running about for a long time. I hear and argue that null hypothesis significant testing has not only failed to support the advance of psychology as a science, but also seriously impeded it, right? So it's not just like, oh, hey, this has some stuff that's bad, or people misuse it. Sort of serious consequences for our ability to grow our field and make reasonable interpretations and sort of understand human behavior in different aspects of things. Okay? Even though this is the basis of our knowledge and theory, misuse, misinformation, misinterpretation is the norm. Procedure criticized on sort of both methodological and conceptual grounds. Criticisms in the fundamental logic of null hypothesis testing. Okay? Our scientific question is, this is what we would actually, this is what we want to know. Given these data, given the data that I've collected, what's the probability that the null hypothesis is true, right? Given what I've seen, what's the probability that my null hypothesis is actually accurate? But what we ask with null hypothesis testing is, given that the null hypothesis is true, what's the probability of obtaining these data, right? Seems like they should be it's kind of the same thing, right? But when we actually start to break it down from a logic perspective, it's not. Anybody philosophy majors previously or taking philosophy classes? Enjoyed philosophy? Okay. So so this is familiar stuff, right? If we start to change the rules of our logic in very subtle ways, things start to fall apart very quickly, right? So if I say, if the null hypothesis is true, these data cannot occur. I say these data have occurred, therefore the null hypothesis is false. That is a perfectly logical, that's a fine statement to make, right? If I say, if the null hypothesis is true, these things can occur. It's impossible for this to occur. These data have occurred, therefore the null hypothesis is false. This is the logic that null hypothesis testing is built on, right? The problem is we tweak this just a little bit, and then all of a sudden we introduce flaws in the logic. What we actually do is we say, if the null hypothesis is true, these data are unlikely to occur. We say, well, these data have occurred, therefore the null hypothesis is unlikely to be true. Okay? So we've gone from a definitive into a probability statement, and then everything starts to come crashing down. To see this, right? If we take sort of null hypothesis, start substituting things around, if a person is an American, he or she is unlikely to be a member of Congress. That's a true statement, right? This person is a member of Congress, therefore he or she is unlikely to be an American. Right? Sort of a silly example, but you start to see sort of the breakdown of the fundamental logic, right? Now, if we were to say, if the null hypothesis is true, these data can occur. Well, that's ridiculous, right? They can occur, right? But as soon as we turn this into a probability statement, the whole foundational logic at which this whole inference is built on starts to break apart really, really quickly. It's difficult to see until we start using some different examples here. Okay? Cohen refers to this as the illusion of attaining a probability. So the fundamental logic of the whole entire procedure is just flawed at a very basic level. This wouldn't get past sort of the first step in the field of philosophy but we put on our blinders and pretend like it's not a big deal in psychology and sort of charge on forward. Another problem is this idea of non-equivalent probabilities. Okay, so we've, scientific question again, what's the probability that the null hypothesis is true given these data? Right, that's what we would like to ask. If we put this in probability terms, we're asking the probability of the null hypothesis given the data. Right? But what we actually ask with null hypothesis testing is the probability of the data given the null hypothesis. Right? These are not interchangeable probabilities. These aren't the same thing. Okay? Again, if we sort of give an example, the probability that you speak English if you attend this class is not the same as the probability of you attend this class if you speak English, right? Essentially, that's what we're doing. We're just flipping things around, and when we start to put it into sort of these types of examples, you see, oh, it's, no, these are very, very different things, right? And you can start to fool around with our inference. What we want to do is we want to reject the null hypotheses as a way to conclude that the null hypothesis is unlikely, okay? But if we really want, if this is what we're interested in doing, there's some things that we need to know ahead of time. Mathematically, we need to have a posterior probability, and we need to know the probability of the null hypothesis before we even conduct the experiment, right? Before we even go into it, we need to know what the probability of the null hypothesis is, right? Problematic because we rarely have a good probability estimate for whether null hypothesis is true, okay? But we can use this as an example to try and demonstrate it with some known probabilities to sort of demonstrate what we've got going on and why this is, the entire logic is fundamentally flawed. So, let's say that the base rate for schizophrenia in the population is 2%. Okay? 2% of 2% of individuals in the population will register positive, do actually have schizophrenia, okay? And that's a known population parameter. And so what we've done is we've got a screening measure that gives us 95% accuracy for positive diagnosis. In clinical, we refer to this as sensitivity, 97% accurate for negative diagnosis, the specificity, right? Now, if you tell me I have a test that has 97% specificity, or 97% specificity, 95% positive specificity, clinical psychologists, were you excited about that? You should be. I'm crazy jazzed about that. Like, that's a pretty good test. So I had to inhibit some explicit expletives there. Like, that's a really exciting test, right? And so if we say our null hypothesis is we've got a normal case. Alternate hypothesis is this is a diagnosis, right? Given that the person doesn't have schizophrenia is 97% or 0.97. The probability of someone registering as being schizophrenic when they actually have schizophrenia is 0.95. This is pretty good, right? I'm pretty excited about this, okay? So, if we want to go through and we say, what's the probability of a positive diagnosis, right? What's the probability of the data of our test saying a positive diagnosis if an individual actually doesn't have diagnosis, right? So what's the probability of diagnosis given that the case is normal? Probability of a positive test given a normal case, 1 minus 0.95, right? So this is our probability of a test. When there is one, we take that, we get 0.95. With our hypothesis test, we would say that it would be unlikely to get a positive test in the case that an individual doesn't have schizophrenia, and we would say that this is an unlikely event, and we would say if the test says that they're schizophrenic, they have schizophrenia, right? So people see where I'm getting these numbers from, okay? So basically, what's the probability that our test is wrong? 1 minus 0.95 is 0.05. Right? But this isn't the question that we're interested in testing in our science, right? What we want to do is we want to calculate the probability of a normal case given a positive test, right? The probability that the person doesn't have diagnoses, given our test says they have diagnoses, actually is quite a bit more complicated, okay? To calculate the probability of a normal case given a positive test, we need to know probability of the case is normal times the probability of a wrong test given that a normal case over the probability of a normal case times the probability of a wrong test given a normal case plus probability of positive diagnosis multiplied the probability of a correct test given diagnoses. If we go down through and actually calculate that out, we actually find that the probability of someone being normal and not having schizophrenia in the presence of a positive test actually isn't very rare at all, right? It's actually incredibly common. And so if we go through and we take in this example, say we have 1,000 people, right? If I'm looking at the probability of a normal test given a normal individual, and I take 494, so the probability of a negative test, given that the person is normal, 494 divided by 979, I get 0.97, right? And if I take the probability of a positive test, given that someone has schizophrenia, that's 20 divided by 21, gives me about 0.95, right? What happens though, is if we start taking a look here and we say, all right, the probability of a positive test, given that the person is normal, right, that's 30 divided by 50 gives us this number right here, okay? And so this becomes a problem. This is what we're testing in null hypothesis testing, right? The probability of the data, assuming that the null hypothesis is true. We find that that's very rare. It's very rare that we would find a sample with a mean at this level or more extreme, assuming that the null hypothesis is true. But that's not actually the scientific question we're interested in. The scientific question we're interested in is what's the likelihood that the null hypothesis is true given these data, and we see if we flip that probability around, we go from 0.05 to 0.607, right? And so again, from a basic logic standpoint, we can't just change these and it's like, oh, you're splitting hairs, right? The probability of the null given the data versus probability of the data given the null, seems like we should just be able to flip those things around. We can actually achieve very, very discrepant results given some characteristics of the data, okay? In this case, what accounts for the huge discrepancy in those two probabilities? What's unique about this case?
In
Yeah.
this case, it's wrong. It'd be the base rate.
And you're absolutely right, Zach. This is a low base rate. We're trying to detect a low base rate behavior. Basically, what's the likelihood of someone committing a terrorist attack? I don't know, right? Or the likelihood of someone coming up and shooting up a public place, right? We can find all sorts of things that, okay, yeah, it kind of looks like these are things that are common in these individuals, but people who have those characteristics, by and large, 99.9% of the time don't go and shoot anything up, right? In this case, we've got a problem with base rates, and the base rate of the target phenomena is so low that it really starts to cause a discrepancy, but a nice way of illustrating the very serious and real problems that we have with the logic of our inference here. Okay. So, demonstrates the potential for error using our p-values to infer the truth about the null hypotheses based on the sample data, right? That's not what we're doing. So we're always saying, what's the probability of these data assuming the null hypothesis is true? Unfortunately, that's not the question that we're interested in asking. Other criticisms, right? This is sort of, again, another technical criticism. The null hypothesis is always false. Like the null hypothesis is always false to some degree, right? It can only be true in the bowels of a computer processor running a Monte Carlo study, and even a stray electron can make it false. So if the null hypothesis is always false, what's the big deal about rejecting it, right? If the null hypothesis can never be true, if sort of at a theoretical, very basic standpoint, our test hypothesis is always false, why do we care if we reject it or not? Tukey, it's foolish to ask, are the effects of A and B different? They're always different, right, to some decimal place, right? So Statistical, this is one of my favorites. Statistical significance testing can involve tautological logic in which hired researchers, having collected data on hundreds of subjects, then conduct a statistical test to evaluate whether there are a lot of subjects, which the researcher already knows because they collected the data and then they're tired. Going back to this, right? In this example, so with 25 individuals, we said, nope, there's no effect. We calculated added, another 125, and now all of a sudden, magically, we have a statistically reliable effect. So much of this depends on the size of your data. Basically, all we're doing with the null hypothesis test is asking, have we collected enough people to claim statistical significance, right? And so for a fundamental theoretical reason, the null is always false. Like the null hypothesis can never be true, right? And so Howell talks about a reconfiguration by Tukey asking not whether or not, the question is not whether or not there's no difference. There's always some difference. It's whether or not A is bigger than B or B or bigger is bigger than A, right? And then the magnitude. Or is this a positive relationship or a negative relationship? I don't know. It's not a zero relationship because that's impossible, right? And so problem with this is that regardless of whatever theory we specify, we expect to reject the null hypothesis in the predicted direction half the time. Assuming that we have a sufficient number of individuals, right, we're going to reject the null hypothesis in the direction that we're looking for at least half the time, regardless of why we've postulated that these things, A should be different than A or B should be different than A, okay? And that rejection rate gets higher if the direction starts to be plausible from a theoretical perspective. So I say that my null hypothesis is that sort of this marker will fall on account of space aliens. It did, right? So I'm claiming support for my space alien theory on account of this falling down, right? There are a lot of reasons why this marker could fall down. It could be space aliens. It could be deep ground aliens. It could be tree aliens. There's lots of different, the gravity, I guess, is one of those things in there, right? But sort of, if I can have an infinite number of theories and reasons why something may happen, if all those things kind of converge on the same stuff, then it starts to become increasingly likely that I'm going to reject the null hypothesis, right, in the direction of my theory, even though the theory may not have sort of anything to do with anything, right? So as a consequence, the probability that an incorrect or irrelevant theory will be supported by the results of the null hypothesis approaches 50% as power increases. So we're never going to say there is no difference, because there can't be any difference, right? This relates to Mealy's crud factor. Everything's related to everything else, right? If I get a large enough sample, any two variables that I want to measure are going to be related to each other at some level. You know, I got 10,000 people. I can claim statistical significance for correlations of 0.01, and so it starts to question the point of doing any of this. Final thing we'll finish up here is sort of the tendency for null hypothesis testing to sort of encourage dichotomous decisions. So this is a Cummings example. So we have a pair of studies evaluating the efficacy of a new intervention for insomnia based on a sample of 44. Lucky 2012 notes a statistically significant advantage of the intervention relative to waitlist controls. See a mean difference of 3.61. Standard deviation of difference 6.97, p equal 0.02. Okay. So we say, huzzah, we have an effective intervention. By contrast, no luck replicates this, fails to observe a statistically significant effect in a similar sample of 36 individuals. Mean difference 2.23, standard deviation of 7.59, but our p is 0.22. Okay. So the question is does this pair of studies provide consistent or inconsistent information, and what conclusions can we make regarding the utility of this new intervention? Thoughts on that? If we go through and we take a look at our confidence intervals, right? So luck 2012, we got a mean difference of a little over 3.5. No luck, a mean difference of just a little over 2. Confidence interval, here we don't collect, it doesn't contain 0. So we conclude that we can reject the null hypothesis. Here, our interval estimate does include 0, and so we say we have to reject, right? But if we actually take a look at these intervals, This one just barely grabs 0, right? Now, are my p-values 0.22, I'm not gonna call p-value 0.22 marginal, right? But if I look at my confidence interval, if this is the range of plausible values for my difference, there's a lot more of that hanging out on the positive end than not, right? 0 is a positive value, but it's just an end, right? If we think about this in terms of distribution, it's not a likely in terms of the overall distribution. Huge level of overlap, right? If I'm looking at this, I might say, for my thesis or for my comps, I might say, well, these guys found it, but these guys didn't, so I don't know, data's sort of inconclusive on whether or not this is useful or not, right? That's actually not a very sort of nuanced interpretation of these data. They both look like they're indicating positive effects, but again, if I take your sample of 36 and change it to 50, we've just fixed this, right? And so, again, if we look at our mean differences here, look at our effect size. Our first study found an effect of about a half standard deviation. Second one, about 3/10 of a standard deviation. So we've got a small effect here, a medium effect here, right? But again, based on our dichotomous reject, fail to reject hypotheses, we would say one was successful, one was not. When it looks like one was successful, one was sort of starting to trending in the right direction. But again, both starting to at least provide, at least in a reasonable estimation, some evidence for this intervention. Questions, folks? Okay, we'll pick up these last couple of slides next Wednesday. This should, yeah, we got like 4 slides left, so we've got enough. What I will do is I will post our 4th problem set and have that due next Friday, okay? Keep working on problem set 3. Again, we're gonna be having that due Friday at noon. Make sure that you're turning in, and again with this one, there's probably lots of graphs that you're drawing in and things like that. Make sure that you print off a hard copy, attach your handwork, give that to Tess so we can go back through and sort of make sure that you've sort of got all your stuff. And then if you happen to have something wrong, we can deconstruct sort of where you got wrong. We can mark that up so that you know where your errors were and so don't make them again. And we'll move forward. We're going to get into the pros and cons. Right now, we're doing pretty basic stuff and having pretty regular assignments as we sort of get farther along in the semester. Assignments will become less frequent, but they will get sort of bigger and more involved. So, if you're feeling fatigued with stat assignments, not to worry. I'll start giving you smaller and more involved assignments for too long. So, cool. All right, guys. Folks, let me know if you have any questions. Otherwise, we'll see you later.